Hello and welcome to Toddcast number 12. We're going to cover resonance, and you'll notice it says resonance part one because there is a lot to resonance. It's going to be something that will explain pretty much 80% of all the wow, what happened there questions we'll see in OChem. So, resonance is the sharing of electron density through pi bonds or the pi network, meaning multiple pi bonds can share it, a single pi bond. It's a weird concept at first, but once you get it, it's I don't know, you master it and it explains everything. So we take the word from a physics concept. If you've ever heard of resonance, it's where something can resonate or go back and forth. So for instance, if you have a spring, it can resonate back and forth from compressed to elongated, compressed to elongated. A pendulum can swing from the left to the right. It can oscillate back and forth. It can resonate. Sound, when it reverberates, when it resonates, is wall, wall, wall. You hear that repeated cadence. So resonance, its electron density can go back and forth and back and forth. That's where the term comes from. And so it's not a physics concept, but we at least can use the physics definition to help us understand it a little bit better, perhaps. Okay, so let's go ahead and get started with resonance then. So resonance again, it's the sharing of electron density through an extended pi network, meaning pi bonds. It ends up you need an odd number to get the resonance effect. And I say that now, and eventually we're going to have a few examples where it's actually an even number. So there are some weird exceptions that we'll talk about. But the resonance that we're going to deal with, we're going to start with three adjacent atoms, sometimes five, sometimes seven. But if we draw our p orbitals, so p orbitals represent an open lobe and shaded lobe represents, let's say, clockwise rotation and counterclockwise rotation of the electron. As long as it's going the same direction, then it can be shared, kind of like you can make a lane change into a lane where traffic goes the same direction. And so if I have this arrangement, what this represents is one electron in each means that's a pi bond there, and then the adjacent atom, whatever it is, has a lone pair. Because these orbitals are all lined up in a fashion where one is next to one, another next to another, electron density, this electron can move to the middle, which can cause that electron to move over there. So it can do the following. And just want to represent, so let me go back and again say, if that's a double bond there, it's represented by that. And if this is some atom right here, it's that atom right there with a lone pair. So we represent this physical perspective with just two lines here and a lone pair. So if this electron moves over and that one moves over here, so let's watch it happen. There they go. So now, if this happens, these are the two that only have one each. So the double bond is now over there and this moved. So we represent it by an arrow with two sides. So normal arrow, where we start at the electron pair, which used to be here, and we move it into the middle of the region it's going to be occupying. So it's going to be in a bond, so we draw it as a bond. Equally, we draw the bond turning into a lone pair. So this is a lone pair turning into a pi bond. And this is a pi bond turning into a lone pair. Okay, so there are my arrows. Let me get rid of what I've drawn. So 3, 2, 1, and it is gone. And so this is the arrow just drew. So the lone pair becoming a pi bond, the pi bond becoming lone pair. So it's only dealing with pi bonds, 3 electrons. So it can go back because again, like we say, resonance oscillates back and forth. So lone pair can be here and then it can move back over here. So it's not the end all be all, it's shared across. When we talk about resonance, so just a reminder, in GChem you learned that arrangement from reactant to product is known as an equilibrium. Well, equilibrium means a reactant can react and go forward to form a product can go backwards and form a reactant. So it goes back and forth. This is no reaction. This is just moving electrons from one p orbital to another p orbital. So rather than draw an equilibrium, even though it goes back and forth, we draw a two-headed arrow. So this is a resonance arrow as opposed to an equilibrium arrow. Important to distinguish those because they are not the same thing. Okay, so if this electron moves back over here and this one moves over here, then let's watch. There it goes. We can represent that the same way. So going back, we could say this lone pair goes in and this pi bond. And I need to be careful because I want it to finish at the end at that carbon or whatever atom I have there. So there are my arrows representing it. You have to, absolutely have to start with the electron. So either an atom with a lone pair or the middle of the pi bond. It turns into the pi bond. So right there, I'm going to draw it into the bond. And then from the bond into the atom, because that's where the lone pair is going to occur. Okay, this is your first introduction to resonance. Absolutely imperative that you draw the structures correctly. So just remember, a lone pair can become a pi bond can become a lone pair. Most often, both of those occur as we draw one resonance structure compared to another. What this means chemically is these electrons are constantly moving back and forth. They're resonating. And so we call them delocalized, meaning they're not staying in one spot. They're not staying in one location. They're moving around. So I'm going to use the word, instead of delocalize, I'm going to say resonating. They're resonating. They're going back and forth. Okay, but to speak chemistry, you need to learn their terminology. So localized and delocalized electrons. So notice this structure right here, it had the double bond and the single bond here with a lone pair at the end. Exact thing we just did, literally what we just went over on the previous example, except now it has a methyl group coming off. So if I were to just do this, it literally is the same example we just did, but can be happening on a longer chain. So only 3 of the carbons are involved in the resonance. That fourth one, that extra methyl group that's been added on, not in the resonance. So again, lone pair becomes a pi bond becomes a lone pair. So it moves over. Notice delocalization. It doesn't always come with a charge, but when it does, if it's negative on one side, then the negative has to move over. So if this was a negative charge because of a lone pair, when it gives up an electron, it's going to go up to neutral, where electrons end up become the negative. So overall, if you drew the composite of that, you would say negative here sometimes, negative here sometimes, so partial negative on each side. Notice that that is different than this one. This lone pair right here, there is no pi bond to donate into. There's no p orbital to share into. So it cannot resonate. It's stuck on one atom. It can't resonate over to others. Whereas this negative charge can resonate back and forth. This is a localized charge. This is a delocalized or resonating charge. Okay, it doesn't have to necessarily be a negative that resonates. It can also be a positive. So I want to make this a little more clear, this drawing. I have a lone pair here. Lone pairs become pi bonds. In this case, this is an even number. So after giving a big speech on the previous slide, this is that rare case. And generally speaking, these are oddballs, and the reactivity they exhibit becomes pretty, I don't know, pretty hot or pretty significant. So resonance normally stabilizes a molecule by sharing the charge over a greater area. But if you have just 2 atom resonating, then you usually have a less stable species. But again, we'll get into that as the time permits. So in this case, that arrow is going to come down, representing a new pi bond being made. But this one gave up electrons, so it takes on the plus. This one gained electrons, so it cancels its plus out. But the plus is delocalized. Sometimes it's here, sometimes it's here. So sometimes on O, sometimes on the neighboring carbon. Okay, localized, there's no p orbitals over here. So if I look at this, this has all the H's it can have. So there's no open space for electrons to flow over. It is said to be localized. It is on one single atom, localized. This is shared across two. This is on one single atom. This is shared across three. So delocalized is resonating back and forth. Localized is where it's stuck on one atom. Okay, important to recognize that. So delocalized electrons must be in a p orbital to be shared. So this has to be in a p orbital for it to come over. This has to be in a p orbital for it to come over. So that picture I drew on the previous page, you would have to have, my lone pair didn't come out as pretty as I wanted. You would have to have this and this atom. I'm gonna say this is my O, this is my carbon. And then there's a plus charge here. It represents that, those electrons being shared now into that. When you do that, you end up with the same alignment of orbitals. The orbitals don't change, just electron distribution changes within them. So resonance is just electrons moving around through a pi system. Okay, let me get rid of my drawing. Okay. All right. So this picture here, same thing just drew. So note that that lone pair mentioned is right here. The other lone pair is in an sp2 hybrid orbital because it cannot be in a p in the same place. So if you recall px, let's say px is up, you have another p orbital that has to be py or pz. It cannot be in the same place. So you can only have one p orbital aligned vertically like this. So everything else, sp2 bond here, sp2 bond here, and sp2 hybrid orbital for that lone pair. Okay. So lone pair is in a 2p orbital, so it can overlap, but this lone pair is in an sp2. Okay. Same thing with this compound. So this is called pyridine. I want to draw. This is going to be kind of ugly. Let me make better use of that. So we're going to have pi bond right there, pi bond right here, and then a pi bond right here. That lone pair then cannot be in that. So the lone pair is in a perpendicular sp2 hybrid orbital. So that one has to be in a hybrid. So let me get rid of what I've drawn. I've drawn right in the way. Okay, so there we go, I think. Now it's complete. So lone pair is sp2 hybrid orbital, so it cannot participate in resonance because you already have a p orbital. So it's worth your time to draw the p orbitals, the structures, so go all the way around. They can resonate. Electrons can move around that ring system, but this lone pair, it is going to be isolated. And notice another example of an even number. So I gave you the odd number. Not the best rule in the world. It is usually odd, but you do have systems that are even. Okay. So resonance rules. A couple things that we need to get down pat before we go much further. When you move electrons, the actual atom themselves, which is defined by the nucleus, does not move. So notice electrons move from one p orbital to another, but the atoms themselves, the center, all stayed the same. So if an atom moves, it's a reaction. If atom doesn't move, it's resonance. Okay, only the position of electrons changes, only electrons move. So you don't necessarily have anything else moving. So lone pairs and pi electrons move. Sigmas and hybrid lone pairs do not move. Everything that moves has to be pi related. So pi bonds and lone pairs in p orbitals. All contributing structures must have the same net charge, meaning if you have a -1, it stays -1 like we saw. If it's +1, it stays +1. If it's neutral, it stays neutral. So all resonance structures, if all you're doing is moving electrons and neither gaining nor losing, then you should have identical charge, identical electron count. Second period atoms can never exceed an octet, but they can have less, meaning carbon can make 3 bonds and form a cation. Boron actually naturally has just 3. So second period, you can have less, but you cannot have a 5th bond. So resonance cannot introduce a 5th bond to an atom. Hydrogen can only form 1 single bond, never more, which means it's not really going to get involved in our resonance. Third period elements can have up to 12. They can make up to 6 bonds. So they can have a weird sort of phenomenon where they have lots of pi bonds going on in the central atom. And then always put your lone pairs in because they can be shared. And then if it has a charge, make sure you keep track of where that charge goes. So like the previous examples, we showed the negative moving to the 2 carbons over when it resonated. And then in oxygen, the positive charge moved 1 over, just donate the electron pair in to form the pi bond. So conserve those charges. Again, hopefully you took a picture of that slide. You'll figure it out as you go. So make a list, check those things off as we go. And once you get used to it, it becomes more of a habit, then that list can be tossed in the trash. So again, lone pair becoming a pi bond becoming lone pair is really common. We just looked at that one. So this one donates in, that goes across. So fairly common. Starts neutral, ends neutral. If this is negative, that'd be negative. So whatever charge start with, you also finish with. We did another one where we said a pi bond turns into a allylic plus charge. We did the opposite, but you can have this phenomenon where pi bond can move over. So allylic, weird term to say if you have a double bond, then if you go down this alley, allylic, the next carbon attached is called the allylic carbon or allylic atom, any atom that's bonded to the double bond directly. So an allylic positive charge, if this pi bond moves over, and electrons go here to put out the positive, but when you lose electrons, the positive ends up moving over there. So again, if you have a +1 on the left, you must have a +1 on the right. So I'm going to clean this picture up a little bit and say that these represent, dashed lines represent, you know what, I'm going to try to make it even better. So the solid line represents a single bond, but these dashed lines represent double bond that may be here or may be here. So this is how we represent a hybrid. This plus charge can be at the end on either side, can't be in the middle. So we put a delta plus here and delta plus here that ends up being +1/2 on one side, +1/2 on the other, if it's symmetric like this, if it shares evenly. Okay, you can also have an allylic negative charge. A lone pair can turn into a pi bond. So pi bond can turn into type of positive, a negative can turn into it. So this one is, notice, it's pretty much identical to what we have up here, except now we have a negative. If this donates in, that can move over. So this might be an O-, for instance. That's going to be a fairly common resonance structure. So all I really did out of laziness is I took this drawing here, brought it here, took this one here and put it here, added a negative, and again, it's at each end. So we're going to represent it just like we did here with, let me draw it one time before I erase it. That's a permanent bond. Here's my hybrid bonds. And that's going to be -1/2, -1/2. Okay. Get rid of it and let the real structure come in. And then finally, lone pair can go to an adjacent. We did an example of that one as well, where you have a plus charge in the middle. This come over. Again, you must retain your plus charge. So if you're losing electrons, you're going to pick up the positive. If you're gaining electrons, you're going to lose that positive. Okay, so this is pretty much it. Pi bonds and lone pairs. Lone pairs turn into pi bonds turn into lone pairs, or pi bond moves around. That's going to be the story over and over. The sharing of electrons, sharing is good. Sharing allows, instead of electrons being in one concentrated space, they're spread out. So it becomes less reactive. If you have all your charge in one spot, someone's going to find it and going to be react with it. So it's going to be highly reactive, i.e. unstable. But if you resonate out, you stabilize that charge, you share it. Okay, one change I want to make on this one is there should be one other bond coming off that carbon. So if I have a nitrogen system here with 3 bonds attached and 3 here, sometimes I have a positive charge here in a double bond. Sometimes I have positive charge on the carbon and a lone pair on the nitrogen. So let me change this to being nitrogen. And then it has an H and a CH3. And this has a CH3. This is a CH3. And you have an empty p orbital and a lone pair in the p orbital. That's what this represents over there. Okay. So best way to get good at this, you have to practice. So here are structures, they're drawn out for you, and we have to figure out how that charge moves around. So we have a negative charge here that can donate in. But if I compare this structure to this structure, let's see, if I look at this, this looks the same, so nothing happened here. This has 2 lone pairs, now has 3. So a lone pair finished here, pi bond went away. So it had to be a case of a pi bond becoming a lone pair. A pi bond to lone pair. Okay. In the second step, let's compare. This 3 lone pairs and negative charge stayed the same. This carbon went from positive to now a double bond. This negative turned to neutral. So you have a pi bond. So in this case, you must have had a lone pair come in. I chose that one just because that's where I haven't put my pen down. You would probably, to make your life easier, draw it from that one. In fact, let me do that. Let me stay consistent. It really doesn't matter, but I want to do it the way that's easiest. That comes in, this negative goes away, this positive goes away because you end up with a bond there. So this is a case where a lone pair became a pi bond. Resonance arrows. The reality is, this is probably going in as this one's coming out. It's probably happening simultaneously like the original picture. This is our resonance hybrid then. Let me get rid of my drawings. So notice it has a delta minus shared equally because of the symmetry here. O and O, there's nothing weird going on. That means this negative could be here or here. It's just as stable up here as it is down here. So half the time up here, half the time up there. So -1/2 there, -1/2 there on average. Okay, a little more complex picture, I think. We'll see how this works. So let's see what happened to nitrogen. Nitrogen was totally happy, 3 sigma bonds in a lone pair like it wants. Lone pair gone. So if the lone pair is gone, then that must be donating in to form this pi bond. The problem is now that this carbon right here would have 2 bonds to O, now 2 bonds N and 1 bond over here. You cannot have 5 bonds. So as the nitrogen donates electrons in, this O has a gain in that lone pair. So I'm going to start in the middle of a pi bond, finish an atom to represent a lone pair. So I went from a lone pair, lone pair, lone pair to now no lone pair and 3 lone pairs. So lone pairs are conserved. Positive and negative, we're going to pick that up when we do future resonance examples. But again, charge is bad. You don't want charge. So this is actually a more stable resonance structure. This is what's going to be known as a minor contributor, meaning 90% of the time it's probably like this, 10% of the time it can be like this. But that 10% is enough to change its reactivity, change its behavior. So I've chosen an example, what's known as an amino acid or dipeptide. So this used to be one amino acid, this is a second amino acid, and they've come together So you can have a peptide linkage with resonance. Okay, to draw the arrows correspond to the following resonance structure conversions. Ooh, this one looks a lot more complicated. So let's see where things are. This O stayed the same, so I'm not going to do anything with it. This nitrogen is changing, it became positive, so it must be losing electrons. So lone pair becomes a pi bond. That's going to be this lone pair coming in. But again, that's going to give 1, 2, 3, 4, 5 bonds of this carbon. So simultaneously, that is going to break. So I start in the middle of the bond and draw the arrow to finish at that point. So lone pair becomes a pi bond turns into a lone pair. Okay, I'm happy with this. This now puts a positive left behind in its wake, a negative lands there. In the second half, there's no lone pair in the final compound, so this lone pair must be donated in from the atom into the bond. So that's a lone pair becoming a pi bond. And again, that would be 1, 2, 3, 4, 5 bonds of this carbon, so it can't have that. So it is going to have the electrons that start at the pi bond, finish at the top. So notice it's the same story over and over and over. You just have to pay attention to detail where it starts and where it finishes. So in the end, this negative charge is now gone again. Pi bond is here. And this pi bond up here turned into a lone pair, which is why we see 2 lone pairs turning into 3 lone pairs. Practice these. Go back, draw these on a piece of paper and try them from scratch. You can always double check what the answer is. So on this one, the resonance hybrid, the one that combines all 3 resonance structures, has a delta plus on the N and a delta minus on the O. This becomes really significant in biochemistry where you have compounds have a lot of O's and N's. That'll dictate how they hydrobond, how they interact. Okay. This one, at first glance, it may not seem like much happened because you don't see charges moving around. So lone pairs aren't becoming pi bonds aren't becoming lone pairs, but pi bonds are moving around. So notice the pi bond is here. It used to be here. It's here, it used to be here. So simply what happened, this pi bond moved from middle to middle, middle to middle, middle to middle, meaning it can resonate around. This is where the term resonance comes from. These electrons can move all the way around the structure in one direction, another direction. They can delocalize around the ring. So you could see it represented by dashed lines, meaning it's a resonance hybrid, or sometimes we draw a circle. I am okay with whichever way you draw it. There are some chemists who are upset the circle doesn't represent anything, but it really does. It implies that there's a ring current associated with this. Could be helpful, but these all represent the same thing. This is probably the way you end up seeing it most of the time in your textbook and in this class. Okay. Lots of these. Oh boy, this is going to be a lot of fun. Lone pair becomes a pi bond becomes a lone pair. So here it is, every, other, every. So it goes to every other, it jumps over. So it went from this point here to every other. So lone pair, because it's negative, becomes a pi bond becomes a lone pair. So it puts a pi bond here, check. It's a lone pair up here, check. So the second one, it goes from this position to 1, 2 away. So it goes from here to every other. So this lone pair can go into the middle of that bond. And in turn, that's going to be 5 bonds on a carbon, so it needs to move that pi bond to there. This lone pair goes every other, so it ends up there. So it's going to move into the center of that pi bond. Pi bond is going to go up there. This is becoming really redundant. Same thing over and over. So finally, same story. This is going to move every other, so it ends up down there. And lo and behold, once it does that, it could potentially move back to its original position. Meaning this negative charge can resonate all the way around, go from position 1 to 3 to 5 to 2 to 4 to 1, go all the way around. Notice the symmetry. So this resonance structure will be symmetric. So all of them in the hybrid will be uniform. Yet another one. So this cyclopentadienyl is going to be really common. So cyclo, 5 carbons pent, diene, ill because it's going to be negatively charged. But we get to it, that'll become just a common structure. So that's going to be familiar soon. The squadino group, as it's sometimes called in bio, is a case where you have a plus charge that can be shared across 3 nitrogens through resonance. Lone pairs become pi bonds become lone pairs. So have a lone pair turn to a positive, so that lone pair must have been lost. Have a pi bond here, the pi bond is gone, turns into a lone pair. So lone pair into pi bond into lone pair. The arrow always finishes as a new pi bond or a new lone pair. It always starts as a lone pair or a disappearing pi bond. They go from this structure to this structure. Again, let's keep track of what we had. Lone pair is a plus charge. So that must have been lone pair donating in. Pi bonds of carbon, so the pi bond has to break. The middle up to the atom. So just make sure you draw the arrows correctly. That's a really big thing when emphasized. So this group can have resonance hybrid where you sometimes double on there, sometimes there, sometimes there. So a third of the time here, a third of the time here, a third of the time here, roughly, it ends up double bonds are a little more stable here and here. So it might be 32%, 34%, and 34%. Okay. Lots and lots of examples. This only comes through practice. So this is our introduction to it. Soon we'll look at it as a stabilizing feature. So resonance will be with you every single day of your OChem career. So hopefully it went well. That said, going to tie this one off and say thanks for being here. See you the next Toddcast. Bye.